Today we're talking about an introduction to factoring. So we've talked about monomials, polynomials, how to perform operations on them. And today we're going to start talking about how to factor, which is kind of a new operation. But before we go too far, I want to talk about factorizing, prime factorization specifically is the example I want to use. So if we look at some examples of some factoring, I could say, what is the greatest common factor between two numbers, right? So GCF is greatest common factor. And a factor is just one thing that you can multiply into something else. So what's the greatest common factor between 18 and 36, for example? So you may remember, in order to do this, we would say, well, let's go down and find two terms that both go into a number. So 9 times 2 gives me 18. I can't make 2 any smaller, but I know that 9 I can break down into 3 and 3. So I could rewrite 18 as 2 times 3 times 3. 36 I know I could write as 6 times 6, but each of these 6's I can break down into 3 times 2 or 3 times 2. So I could rewrite 36 as 2 times 2 times 3 times 3. So I could rewrite each of these as just a set of factors. And these are all prime factors. I can't make them any smaller. So the greatest common factor then would be the product of any factors that are common to both numbers, or any factors that are in both numbers. So if I look, I see that there's a 2 in 18 and a 2 in 36. So that is a common factor. There's a 3 in 18 and a 3 in 36. So that is a common factor. And again, there is a 3 in 18 and a 3 in 36. So all of these numbers are common factors to both, and the greatest common factor is if I multiply them times each other. So 2 times 3 is 6 times 3 equals 18. And actually the greatest common factor to 18 and 36 is 18. I could look at another example. If we had 60 and 48. Maybe. You might already know what the answer is, but let's go through the same method again. I can write down 60 and say, well, that's 6 times 10. 60 I can break into 3 times 2, and 10 I can break into 5 times 2. So I could rewrite 60 as 2 times 2 times 3 times 5. And I'm putting these in order just because it's a convention. Right? Mathematicians, when we write out these prime factorizations, we write them out in order. But what I really need is just to know what those numbers are. 48, you may know, is 4 times 12. Well, I can break 4 into 2 times 2 and 12 into 3 times 4. Now I can break that 4 again into 2 times 2. So I see 1, 2, 3, 4 2's. A 3. And actually that's it. 2 times 2 times 3 times 2 times 2. So I can then read, and my greatest common factor would be 2 times 2, because I have them in both, times 3, because there is a 3 in each. So my greatest common factor is 12. And one thing I want to point out is I could rewrite it by taking all of these terms as a 12 and multiplying by what's left over. 12 times 5 equals 60. If I took 2 times 2 times 3 and got 12, I would have left over 2 times 2, which is 4. 12 times 4, or the greatest common factor times what's left over, gives me 48. Okay? So this is just a quick review of the greatest common factor. Now that we're algebra students, we are going to add some variables into this, right? Not only can we look at factors of numbers, but we can look at factors of monomials. So for example, x squared is actually a product. It is the product of x times x. 3x squared is the product of 3 times x squared, which is the product of x times x. So I could rewrite these monomials as a product of factors. I can break them down into the factors. So for one more example, what if I had 12a squared bd cubed? How could I break that down? Well, I know that the prime factorization of 12 is 2 times 2 times 3. A squared is a times a, b, and d cubed is d times d times d. So this would be the prime factorization of 12a squared bd cubed. So once I know that, I can apply the same skill to find the greatest common factor of two monomials. So if I had 4yz and 2y squared, well, this could break down into 2 times 2 times y times z. And 2y squared can break down into 2 times y times y. So the GCF then, I see a 2 in both factorizations. I see a y. And actually I don't see anything else. This 2 here is not matched with anything on this side. There's certainly no z. And even though there's an extra y here, I can't match it with a y on this side. So the greatest common factor is in fact 2y. So we're going to keep that in mind and look at another one. 12q squared r to the third s and 3q r squared. I'm going to look this time in bigger chunks. I have a 12 and a 3. What is the greatest common factor between 12 and 3? What's the biggest number that can go into both of those? Well, I could do a prime factorization, but I also know that 3 itself goes into 12, so it's just going to be 3. Now if I look at the q squared piece and the q piece, if I think of these as two different exponents, q to the first power is a lower exponent than q squared. So q to the first is going to be the largest that can go in. I have r squared and r cubed. So that's r times r, and this is r times r times r. So r squared is fully a factor of r cubed. There is an s in this product right here. There's no s on the other side, so I cannot include that. And my greatest common factor is 3qr squared. What about if I had, I keep skipping to that page. What about if I had 16u to the fourth VW and 12u to the fourth? If I have these, what is my greatest common factor? Again, I can look at the 12 and the 16. And the greatest common factor between those two is 4. Okay? I could rewrite this as 4 times 3 times u to the fourth, and I could rewrite this as 4 times 4 times u to the fourth times v times w, so it's a 4. Now here I have a u to the fourth and here I have u to the fourth, so that is common to both terms. I don't have any v's, I don't have any w's on this side, so none of them are included. My greatest common factor is 4u to the fourth. Again, I could take this and rewrite 16u to the fourth VW as a product of these two. So 14u to the fourth, 4u to the fourth, I pull out. So there's my 4 and there's my u to the fourth. What's left over? I still have a 4, I still have a v, and I still have a w. So I can write 16u to the fourth VW as 4u to the fourth times 4VW. On this side, if I write 4u to the fourth, I've taken care of these two. What's left over is just 3. So I can rewrite each monomial as a product of the greatest common factor and all of the remaining factors. So let's look at one more. What if I have g squared and 8h squared? What is the GCF in this case? Well, I have kind of a hidden 1 right here, right? Invisible math. I have a 1 and an 8. What is the greatest common factor of 1 and 8? 1. Okay. I have a g squared in this term, and there's no g's here, so I cannot bring any g's down. Similarly, I have an h squared on this side, but there are no h's in this term. So this set of numbers, the greatest common factor is just 1. It's just 1. These terms are what we call relatively prime. There are no common factors between them. Neither one is actually a prime number, but to each other they share no common factors. So let's look at some of these sets of numbers again. For example, we had 4yz and 2y squared. I can put those together in a polynomial, and now I can use this greatest common factor to factor the polynomial. So I looked at these two terms individually and said, okay, the GCF is 2y. That means that there's a 2y inside each of these terms that I can factor or reverse distribute out. So if I pull out that 2y, if you remember, what was left is 2, because 2 times 2 makes 4. There's my y and z. I'm going to bring down my plus sign. 2y. What I have to multiply 2y by is y. Y times 2y gives me 2y squared. And this is my factored form of that polynomial. I have taken the GCF and reverse distributed it to take it out. If we look again at the 12q squared r cubed s, and this time we're going to go ahead and add 3qr squared. We said before the GCF between these is 3qr squared. That means that that factor is in both of these terms. So if I pull it out, what's left over, 3 times 4 to give me 12, q times q to give me q squared, r squared times r, and then s, plus this time 3qr squared. That's entirely this whole term. There was nothing left in that common factor, so it's plus 1. That is my factored form. I have factored that. But let's see what happens when I take these relatively prime terms. If I have g squared plus 8h squared, what can I do to factor those? The GCF in this case was 1. There is nothing I can factor out. The book likes you to rewrite it as 1 times g squared plus 8h squared. You cannot factor if there is no common factor. Cannot factor out a monomial if the GCF is 1, right? All that you can pull out is 1, and you end up rewriting the same thing. So just one last reminder. If we look at our last example, we had 16, I think we did this, 16u fourth VW minus 8u to the fourth. If I look at these, my GCF is 8u to the fourth. So I will pull out 8u to the fourth. What is left over now is 2. 8 times 2 gives me 16. U to the fourth is there, so I'm going to copy my VW. Now this sign is minus, so I'm going to keep the minus sign, and then 8u to the fourth is completely pulled out, so it's minus 1. When you have this negative sign, just look for the greatest common factor of the positive terms. All right? You don't have to consider the minus sign. So just look for the GCF of each term and carry along the minus sign. Right? Or minus sign. Subtraction sign. All right, so there you go.